Hi class, welcome to Lab 13 for week 13. We are just a couple of weeks away from being done. So today we're going to start off talking about logarithms, and we're actually going to go over something that I kind of touched on in the previous week's lesson for 12. And we're going to talk about the change of base formula today and how we can use it to solve problems. So for 4.3, it says, do you know that what exponent to raise 32 to and get 8? Okay, another way to ask this question is to ask odd. Okay, another way to ask this question is to ask you to evaluate log base 32 of 8. And although you might not be able to evaluate log 32 of 8 mentally, you should be able to evaluate log 2 of 8. You should also be able to evaluate log 2 of 32. So how do we go about doing this? Okay, so if we do log 2 of 8, and we technically set it equal to x, because we're solving it, we do our little circle method, right? We do 2 raised to the power of x is equal to 8. And we need to know what exponent will give us 8. In this case, I know that my exponent is 3. So I know that technically it is 2 cubed equals 8. Now I do the same thing for this next one. I get 2 raised to the power of x equals 32. And I need to know 2 raised to what power will give me 32. And in this case, if I'm not mistaken, I believe it should be 5. So I know that 2 raised to the power of 5 is 8, right? So we can say x is 3 for the first one, and of course our exponent is 5 for the next one. Okay, there is a formula called the change of base formula, which, as you can see below. And I showed this to you pretty briefly in the previous week's lesson. It says for any positive number a, b, and c. And with b cannot be equal to 1 and c cannot be equal to 1. This is called the change of base formula. This is where I told you in order to take a logarithm and plug it into your calculator, we need to be able to change it up so that we can make it a base of 10, because our calculator only does a base of 10, so that we can plug it into our calculator. So what we say is we do log of a and log b at the bottom. You actually don't need that c. It's an understood 10. But you'll go log of a divided by our log of b. If you can't remember who goes on top, remember the larger number goes on top, the smaller number goes on the bottom. And I mean that literal size of the number. And it says, according to the change of base formula, log 32 of 8 can be written as log of with a base 2 of 8 divided by a log 2 of 32. So we're going to actually take this and plug it into our calculator. So we're going to do that's overly complicated. I don't like the way that was explained. Technically, those 2's don't even matter. We don't need them. Really, all you need to do is say log of 8. Oops, hang on, sorry. Log of 8 divided by log of 32 equals 0.6. Don't give me the decimal. We go math, and we hit enter, so that it puts it back into the fraction, which happens to be 3 over 5. So using this formula, we have found that log 32 of 8 is equal to 3 over 5. Or in this case, because it is a nice, clean decimal, we can actually say that it is 0.6 or 0.6. Okay, and according to the change of base formula, log base 32 of 8 can also be written as log 8 over log 32, or it can be natural log of 8 over natural log of 32. So if we wish to use your calculator to evaluate a logarithm, you can use the change of base formula to rewrite it using logarithms with base of 10 or we can use a base of e. Sorry, I do cursive. Sorry, I do cursive. Sorry, I do cursive. Sorry, I do cursive ln's. This one is a log of 10. Okay, so we're going to try using our calculator to the change of base to simplify log 32 over 8, which we've kind of already done. It says use the change of base formula to approximate log 2 of 14 to 3 decimal places. Very important there. So what we'll do is we'll rewrite it. We'll say log 14 over log of 2, right? So we'll do log 14 on top divided by log of 2. And in this case, it tells you to do decimal points because if I tried to take that and flip it back into a fraction, you're not going to get one. So to 3 decimal places, we're going to get approximately, sorry, let's use our little approximation symbol there, approximately 3.807. Now for log 3 of 82, we're going to do the same thing. We're going to go log, large number on top, log, small number on the bottom, and we will get log of 82 divided by log of 3. And our, sorry, that's not going to be equal. That is approximately 4.011 to 3 decimal places. All right, so now we're going to talk about properties of logarithms. And one of the properties that we use in order to solve is going to be the one-to-one property. What that means is, given an equation, you have a log base A equal to another log base A. Very important. They have to be the same exact log and base. Then what we'll be able to do is take and drop them and set them equal to each other to solve. All right, so we're going to do this in practice. All right, we have a log x equal to a log 35. Remember, if there's no base number there, it's an understood base 10. But in this case, all we have to do is look at it and go, oh, okay, well, I have a log equal to a log with the same base. I take them and I can drop them so that I get x equals 35 as my solution. Now again, I have log 2x minus 1 equal to log 58. Technically, the logs have the same base, so we get to drop them, set them equal to each other, and now solve for x. So that I will add 1. So I get 2x equals 59 divided by 2. So I get 59 divided by 2, which I believe I can't do, so I'm going to have to just leave it as 59 over 2. Yeah. Or I can say that x is approximately, well, x is 59 over 2. Or I can say that it is 29.5. You can also take and plug them back in to your equation on both sides to figure out if they become equal to each other. Let's see, if we have our next one, we have a log 4x minus 10 equal to log 9x plus 16. Again, my logs are the same, so I get to drop them. And I'm going to set 4x minus 10 equal to 9x plus 16. And then I'm going to start moving everything around. I'm actually going to move, you can either move the x's to the left or you can move the x's to the right. It does not matter. I'll move my x's to the left. And then I will move my 10 to the right. I like to do this in one step if at all possible. So I know these have moved. 4x minus 9x is minus 5x equals 16 plus 10 is 26. Divide by that negative 5. I don't think that this reduces any further, so I know that this is going to be x equals a negative 26 over 5 as my solution. So now we're going to move on to solving problems when they're not two logs equal to each other. So we have to go about using different properties to get the logarithm by itself. So first step for A, we have 8 natural log of x equals 32. Well, first of all, I need to move that 8 that is in the front to the other side. That is 8 times ln. So I know I'm going to move it by division. So that I'm left with ln of x equals 32 over 8 reduces to be a 4. So now, how do I get rid of a natural log? Well, it's quite simple. I actually just take it and raise it to the power of e on both sides. Or, well, actually give it a base of e so that the natural log is gone. And I'm left with x equals e raised to the power of 4. He's going to be my solution. All right, for B, we have a log base 3 of x equals 5. In this case, nothing needs to move or anything like that. I'm actually going to rework this logarithm so that it becomes an exponential. So remember, there's nothing in the front here that needs to be moved. So now I can just go about working him by solving logarithms. So I get 3 raised to the power of 5 equals x. Well, if I don't know it, 3 raised to the power of 5 equals 243. So x equals 243 as my solution. You could give both of these as an option. All right, C, a little more complicated. I have a logarithm, nothing's in the front. So I know I'm going to have to use the circle method so that I get 3 raised to the power of 14 equals everything inside. So equals x minus 1. Now to solve for x, of course, I know I'm going to have to do plus 1. So I will get 3 raised to the power of 14 plus 1 equals x. Now, if you have to, you can put it into your calculator. 3 raised to the power of 14 plus 1. Enter. Oh, large number. So you could give me that number. You could leave it as 3 raised to the power of 14 plus 1. It doesn't matter. So I will also say that this is, what is that? 4,782,970. Right? Give me both answers if you feel so inclined. Oh, what is going on with my... Sorry, guys. Hopefully that'll come back up before I'm done. There it goes. Okay. Now, look at D. I have 2 things in front of my natural log. I have addition occurring, and then I also have multiplication occurring. So I'm going to move the addition first. So I'm going to take and move that 5 to the other side by subtracting him, so that I get 10 ln of x minus 1 is equal to 20. Now I will also have to divide both sides by that 10 that's in the front. So remember, divide everything on one side, everything on the other. So I get an ln of x minus 1 equals 2. And remember, how do I get rid of a natural log? Well, in this case, I have to give it a base of e on both sides so that that natural log is gone. And I get, I'm going to bring my problem up here. I get x minus 1 is now equal to e raised to the power of 2. To solve for x, I'm going to add 1 to both sides. I cannot physically add e squared and 1, so I'm going to say x is equal to e squared plus 1. And here's my answer. E. Okay, E is a little bit more complicated. So, this is where you need to know your properties of logarithms. Remember, if they are being added, then technically they are being multiplied. I'm not sure if your other instructor kind of went over the rules of this or properties of logarithms, but if you have two logs with the same base, x plus log, 5 of y, this is technically the same as saying log 5 of x times y. So we can actually take and condense our logarithm when they are the same exact base. Remember, both these have a base of 5, so they can be combined. Same goes for subtraction. So if I have a log 5 of x minus a log 5 of y, I know that these can be condensed into a log 5. X minus y, like addition is multiplication, subtraction is division. So we go over here, we look at our logarithm, we say, oh, okay, they have the exact same base. So I'm going to condense them into one logarithm so that I can then say that this is a log of 5 with an x times x plus 4 equal to 1. Now I can take and use my circle method since I have one logarithm. So I get 5 raised to the power of 1 is equal to what's inside the parentheses, which is x times x plus 4. Don't do this. There we go. 5 raised to the power of 1 is equal to x times x plus 4. Come on. There goes x times x plus 4. So that would give me 5 raised to the power of 1 is 5. And then I get x squared plus 4x. Move the 5 to the other side so that I can solve it to get x squared plus 4x minus 5. I'm going to actually have to factor this. I'm going to go what times what? Gives me a negative 5, but adds to be a 4. Well, that's going to be an x plus 5 and an x minus 1. So that when I solve, I get x equals a negative 5 and a positive 1. But I always have to plug it in and check. And a good rule of thumb is if you plug your x back in and your logarithm gets an answer of negative 5 or a